A small confession, I always feel a little bit silly coming up here giving a lecture as an expert in crystallography, because everything I know about crystallography I really just learned over the last 5 years during my postdoc with Amy Rosenzweig. So I really have to acknowledge her, as well as 2 years ago at this workshop, Tom Lawton, one of her graduate students, and I put together this lecture and a practical exercise, and I still use a lot of the material that Tom provided in the lecture this year. And then this time, for the hands-on exercise, we have a visitor from Germany, Oliver Einzel. He developed the hands-on exercise completely by himself. And it's a really fun activity. I'll just give you a quick preview and tell you about all the different things that we'll do. And I really sort of designed the lecture today to provide the best preparation possible for this activity, because I think it's really ambitious. It's a lot of things to get done in 2 hours, so hopefully this will make it easier. In the hands-on exercise, we're going to do a complete de novo structure determination of a thermophilic 2-iron, 2-sulfur cluster ferredoxin using multiple anomalous diffraction phasing. And so the activities that you guys will do, will process a diffraction data set, actually several diffraction data sets. We'll derive the heavy atom positions in those data sets, use them in an automated phasing pipeline, and then perform a model building, either an automated or a manual model building exercise, followed by refinement. And in addition to Oliver preparing the data and designing the activity, one of my graduate students, Andrew Mitchell, did a lot of the troubleshooting, make sure that everything works on our system. And so I'm grateful to the two of them for handling this part of the crystallography portion of the workshop. So X-ray crystallography is really just one of the tools available to visualize macromolecules. A few others are listed here. One of these we'll hear about this afternoon from Nozomi Ando. And I guess the rationale behind selecting a particular technique to visualize a macromolecule of interest is dictated by perhaps 3 things: the resolution of the information that you need to get out of the technique, the size range that's appropriate for the type of technique, and how easy it is for you to use. And so I think X-ray crystallography is really quite versatile among these techniques in that it's useful with a large range of molecular sizes. High resolution information is possible in many cases. There's an ongoing effort to improve accessibility to general users. So I would even put out there that any of you in the audience that would like to solve an X-ray crystal structure yourself without the aid of a collaborator, you can probably do that. And I've tried to provide some resources here for that and to highlight some of the special issues associated with structure determination metalloproteins. And additionally, there are many widely available tools to view and assess the results of crystallographic experiments. Many of you are familiar with these tools, I'm sure, to view the molecular models that come out of crystallographic experiments. But one thing that I'll maybe try to give you a sense for, and those of you that participate in the hands-on activity will also get to use some of these tools, but there are also quite a lot of resources available for viewing electron density maps. And I think this is something that maybe not a lot of people appreciate or use, but it's really important. I think crystallography is maybe sort of unique in that it's usually only the model that's reported or described in a manuscript or used. But the electron density maps are really what contain information about the experimental data. And I think it's less likely that a user of a molecular model will go in and actually look at the data that generated that model. All published molecular models that come from crystallographic data are deposited in the protein data bank. I'm sure most of you are familiar with this. And this is just to perhaps remind you that the outcome of a successful structure determination experiment is a text file that contains a listing for each of the atoms in your model, an XYZ coordinate for the position of that atom, an occupancy of that atom, and a temperature factor. The temperature factor is actually a measure of disorder of that atom in the model. And this is really the final product of the experiment. There are a lot of tools available for viewing these models. I've listed a few links. PyMol is perhaps the most well-known, but there are a few others. In the hands-on activity, we will use Coot. Coot is really a nice tool because it It allows you to work with both the model and the electron density map, the experimental data at the same time. There are a number of other resources as well. This is just an example, it's a little dark, but of electron density map for a metal ion in a metalloprotein crystal structure. And this just shows you perhaps some of the differences. These are very similar in terms of the molecular model, but the electron density maps are quite different. And so this is an example where being able to go in and view the electron density maps might help you gauge the accuracy of the model. These are some tools available for viewing electron density maps. All structures that are deposited, at least relatively recently, also required that you deposit structure factors that are required to calculate electron density maps. So for any model that's available in the PDB, you can go in and look at the electron density map associated with that model. And these are some tools available for viewing those maps. Okay, so some limitations associated with crystallographic experiments. A crystallographic model gives you a static snapshot of what is really, in real life, probably a very dynamic molecule. The model is an average of all molecules present in the crystal lattice, so it really is an average technique. It's not a single molecule technique. Crystallographic models are often obtained under specific conditions that can be far from biological relevance and can affect structure. Structure can also be influenced by data collection, and this is especially true for metalloproteins, especially those that are oxidized. They're very susceptible to reduction during X-ray exposure. And the resulting model is, like any experiment, an interpretation of data made by a scientist, by a human being. And I think this is really perhaps the motivation, if you're using a crystallographic model for other experiments, to go in and look at the electron density map and make sure that you agree with the interpretation made by whoever generated that model. Some benefits to using crystallography to characterize metalloproteins. X-ray crystal structures are often important starting points for other types of experiments, including mechanistic study, computational studies. They're also important inspiration for synthetic models. They are useful as models for other biophysical techniques. They provide important information about the location, the identity, and the stoichiometry of metallocofactors that often can't be gained any other way. They also provide important information about the geometry and identity of both amino acid ligands and exogenous ligands. In many cases, they've been important for elucidating the structure of complex metallocofactors, and they also provide important context for other structural analysis methods. So some limitations at X-ray crystallography, relative to a lot of the things we've heard about over the last few days, is really a pretty low resolution technique, especially for doing things like measuring bond distances and angles. So for getting really accurate measures of metal ligand bond distances and geometries, crystallography is often not the most accurate technique, especially if the resolution of the crystallographic data is moderate or low. It can be difficult to determine oxidation states unequivocally from crystallographic data alone, although I'll show you an interesting example later on in the talk where you can get some information about oxidation states in crystal structures. The oxidation state of metal centers is also can be influenced by the data collection process, by X-ray radiation of the cofactors. Okay, so I thought I would talk first just a little bit about the underlying basis for how crystallography works, and then I'll go into some of the more specific aspects of the experiment, especially the things that we'll do during the tutorial. So the way that we use X-ray crystallography to visualize macromolecules is really fundamentally very similar to the way that we look at anything that's smaller, the way that we look at anything in general. And that's that we take an object, we shine light on it, light is diffracted by the object, and in things like microscopy, we can use a lens to generate a magnified image, visualize the image directly in this type of experiment. The issue, though, is that the wavelength of light rays used to visualize the object of interest must be appropriate for its size. So macromolecules, because they're small, if we want to visualize atomic level structure in them, we have to use X-rays. X-rays are the appropriate wavelength. We don't currently have a way to directly visualize objects using X-rays. And the other issue is that single molecules diffract X-rays relatively weakly. So in X-ray crystallography, the reason that we require a crystal lattice to visualize molecules is because it amplifies the signal associated with X-ray diffraction. And then because we can't focus X-rays by lenses, we have to solve the structure using mathematical methods, mathematical reconstruction methods. And nowadays, this is greatly facilitated by computers. Okay, so there's really 5 parts to a crystallography experiment. The first is producing a biological sample that's appropriate for crystallization and for collection of X-ray diffraction data. Once we collect X-ray diffraction data, we have to solve the structure. And then once we have an electron density map from the structure solution process, we build a model into that and then validate it and report it. Other resources, particularly for those of you that might be interested in solving your own X-ray crystal structures, there are a number of workshops and courses available. Most of these are associated with synchrotron facilities at national labs, and these are actually really great because most crystallographers nowadays collect data at synchrotron sources, and these workshops not only provide an introduction to crystallography, but they also give you exposure to how to use the facilities at a synchrotron and tell you how to gain access to them yourselves. So these are 2 that I know of that are really great, that I have participated in, or I know people who have participated in them. There are also courses associated with things like Cold Spring Harbor and Woods Hole that focus on structural biology as well. So in preparing this lecture, I made use of these 2 textbooks as resources. These are also really good if you're interested in learning more about crystallography. And then Surview from my postdoc advisor's lab is also a really good introduction to some of the benefits and issues associated with using crystallography to characterize metalloproteins. Okay, so I'll say just a few words about biological sample production. Maybe I'll first highlight that this, I think, is sort of an underappreciated variable in crystallography. And in my own experience and in my own lab now, we actually spend quite a lot of time identifying the most appropriate biological sample for crystallography. If we aren't successful in getting crystals of our sample, this is the step that we often come back to. So first step is selection of an appropriate sequence or construct, identifying an appropriate organism to generate your protein of interest. With bioinorganic systems, incorporation of the appropriate cofactor is often a major issue, and I'll give you just 2 quick examples of some ways to ensure that the correct, fully assembled, fully occupied metallocofactor is incorporated into your system. And then finally, the method by which you purify the system, presence or absence of any affinity tags or artificial sequences in your construct, also a very important variable in ensuring that you generate a sample that's appropriate for crystallization and data collection. And I think an important part of this is that you have to have a mechanism to assess purity. The standards for purity are often higher in crystallography than for other techniques. Polydispersity, this is a measure of whether or not you have a single species, single oligomeric species, monomer, dimer, something higher order. It doesn't actually really matter what it is, I guess, except that it's important typically to just have one species. Mechanisms of assessment of this variable include gel filtration, chromatography, dynamic light scattering, things like that. And then it's often useful to assess activity of the sample as well. Most people are interested in characterizing structure of an active system. Okay, so a major issue with bioinorganic systems is incorporation of the correct or fully occupied metallocofactor. In many cases, just simply taking a sequence of interest from a random organism, overexpressing it in E. coli, it will often result in either incorporation of the wrong metallocofactor or something that is not exactly what you want. So one method that has been used is to take advantage of a native organism to isolate the protein. Two examples of this that have resulted in a successful structure determination include methane monooxygenase, both as particulate, which is shown here, soluble forms, and nitrogenase. These are systems for which you have to isolate them from the native organism, otherwise they're not able to incorporate the correct metal center. You can sort of recapitulate this by, if you know the biosynthetic pathway, by incorporating other enzymes associated with biosynthesis of cofactors. This has been used in other systems that require iron sulfur clusters to produce them in a heterologous host. Another way that you can ensure correct incorporation of the appropriate metallic cofactor is to generate an apoform of the protein and then reconstitute either prior to crystallization or after. And one example of this is a class 1A ribonucleotide reductase. This is a system that uses a diferrous center to generate a necessary metallic cofactor upon activation by oxygen for nucleotide reduction. In this system, the diferrous version of the protein is not able to be crystallized. One method that people have used to characterize crystallographically the diferrous state is to crystallize the oxidized form and then chemically reduce it with a reductant or mediator, and that generates this model shown here. Interestingly, this is not consistent with several predictions that were made by spectroscopic characterization of the diferrous state of the protein in solution. And in the Rosenzweig lab, they decided to address this question by crystallizing the apoform of the protein and then soaking ferrous iron. And that generated a different structure that was more consistent with characterization of the state in solution. So in a typical crystallography experiment, the crystallization step is viewed as the hardest part of the experiment. And that's because you have to get your protein to do things that look like this. So I thought maybe I'd start first by just describing a little bit about what crystals are. Crystals, macromolecular crystals, are ordered three-dimensional arrays of molecules that are held together by relatively weak interactions, usually hydrogen bonds mediated by solvent. And so in practice, that means that they're pretty fragile and hard to deal with. They're composed of unit cells. You can think of the unit cell, I guess in a very simplified way, as the box that you draw around your protein in the crystal. These cells are the repeating unit. They have a defined shape, and we define this shape by the length of the axes of the box, the A, B, and C, that we refer to as A, B, and C in this picture, and the angle between these A, B, and C lengths, alpha, beta, gamma. These have an XYZ coordinate system, and the shape of the unit cell, I guess defined by the equalities between the A, B, and C lengths and the value of the alpha, beta, gamma angles, classifies macromolecular crystals into 14 different lattice systems, and these are called Bravais lattice types. So you don't have to know what these are, but this is determining the lattice type is an important first step in analysis of diffraction data. These A, B, and C values are not only, I guess, equalities in length, but they're also identities, and that means that the contents of the unit cell along the A, B, and C axes are identical. Within the unit cell, you could have multiple copies of your protein, and the internal symmetry between copies of molecule or the asymmetric unit in the crystal is part of definition of the space group of your crystal. And this, again, is an important component of successful structure solution. I won't go through what all of the possible space groups are. There are 230. For chiral molecules like proteins, there are 65 possibilities. We designate these by symbols that describe the lattice type and the symmetry operators that define the space group. But I think the take-home message here is perhaps that this is something that we have to assign correctly in order to solve the structure. And this is something that we will go over in the hands-on section. So the crystal lattice is an array of unit cells. It's an imperfect one, and the molecular model that's determined in a crystallographic experiment provides an image of the average electron density in the asymmetric unit. Okay, so how do we actually generate crystals? You can think of crystallization as a slow, controlled precipitation from solution that occurs without unfolding the molecule. We often describe these using a phase diagram where you start with your protein in solution and you add something, usually a reagent that causes protein to begin to precipitate. And you also change the concentration of the protein such that you begin to form aggregates or nuclei. And then the hope is that you do this under conditions where these aggregates form an ordered lattice via slow and controlled growth from nucleation sites. Important variables here include pH, temperature. Precipitating reagents are typically salts. Ammonium sulfate is very common. Salt that's used as a precipitating reagent, polyethylene glycol, small organic compounds like alcohols. Additives are important as well. And in general, these precipitants act by disrupting the hydration layer around the biomolecule, these forced self-association, and the hope is that you do this without affecting the structure. The most commonly used method is vapor diffusion, in which your precipitating reagent is in a well, protein is in a drop that is either on a pedestal that sits above the well or on a cover slip that hangs over it. And the idea here is that you mix your protein with the precipitating reagent and you seal it, and over time water vapor moves out of the protein drop back into the reservoir solution until the concentrations are equal. And it's this slow evaporation process or slow concentration of your protein that facilitates crystallization. I think an important point to remember is that this process can take days, weeks, or months, and your protein or the system that you're interested in needs to be stable over that period. So in a crystallization screen, there's a spectrum of things that you see, and really the only outcome that is appropriate for moving forward into data collection and structure solution is observation of a single crystal. You can often, from things like this, needle clusters, plates, or non-single crystals, further optimize to obtain something like this. But a single crystal is the desired outcome of the crystallization process. Okay, so how do you find the appropriate precipitant? We are not able to currently predict the conditions that result in crystallization of a given macromolecule, so we have to take a trial and error approach. So we use sparse matrix screens to sample what I call here condition space for a given system. These are commercially available. They're often facilitated by robotic setup and monitoring. There are even facilities where you can send your sample and they will do this part of the process for you. But it's often required that you either go back, that if you're unsuccessful in finding the correct precipitant for a given sample, that you have to go back and identify either a different construct or its preparation. Okay, so to me, this is the hardest part of the process. Once you have crystals, usually you get something like this, where there's more than one crystal in a crystallization plate, and you have to isolate one of these. The way that we do that, we use rayon loops that are mounted on a magnetic base. And the base is I guess, appropriate for the data collection setup at the X-ray source. And the reason this is hard is because macromolecular crystals are really small. They're on the order of about 100 microns. And manipulation is really challenging because they're so small and fragile. Crystals are typically frozen in most cases in liquid nitrogen for data collection. They remain that way the entire time. This is actually, I guess, sort of a critical point for working with bioinorganic systems in many cases, particularly those that are oxygen sensitive. What this means is that once you get your crystal frozen in liquid nitrogen throughout the data collection process, it usually remains in a stable state. Okay. So once you have generated a single crystal, the next step is to place it in the path of an X-ray beam and collect diffraction data. We usually collect data either on home sources or at synchrotron X-ray sources. For synchrotron sources, these are actually pretty critical for collecting both high-resolution data as well as for collecting data appropriate for structure solution in the first place. And there are only a few of these in the country. I've shown a few common places that people go to collect macromolecular diffraction data. National Light Source at Brookhaven, Advanced Photon Source at Argonne National Lab in Chicago, and Stanford at Berkeley as well in the Bay Area. So the outcome of an X-ray diffraction experiment is a pattern that looks like this. And there's really, I guess, two pieces of information that we take away from diffraction pattern. The index of every spot that appears as a result of a diffracted X-ray from your crystal. The position we catalog via an index, an HKL index. This is an integer index, and its intensity. Quality of a diffraction pattern is assessed by looking at the spot shape. We measure intensity by integrating across a spot, and we do this with computational assistance, and computer assumes that your spot, in most cases, is a circle. So if you have poor diffraction and you don't see a clear single spot, that can be a problem for computer-assisted measurement of intensities. We also look for evidence of a single lattice, and the other piece of information that we're able to take away from a single diffraction pattern is the resolution limit of the data. Okay, so these are just some examples. It's a little dark, but this is, I guess, an example of poor diffraction where there isn't a clear single lattice. Each spot is a reflected X-ray from your crystal, and it's given an index. Indices provide information just about the type and the symmetry of the lattice. They don't actually give you any information about the structure of your protein. So the positions of the spots solely report on the lattice. It's the intensities of the spots that provide information about the positions of atoms in the crystal. So accurate measurement of intensities is really important in crystallographic data analysis. Indices begin at the origin or in the center of your diffraction pattern, and they increase as you move outwards. And so it's the reflections that are far away from the origin that provide high-resolution structural information. And I'll tell you just a little bit about why that is. Resolution affects the level of detail that you can see in electron density maps, and this is perhaps a really good example. This is a beta sheet structure. At 6 angstroms, there's really no information at all about secondary structure. At about 4.5 angstroms, you can perhaps start to see individual strands, helices, but you really have no information at this point about the structure of side chains. At about 3 angstroms and below, you start to see an increased level of detail about side chains, and below about 2 angstroms, you start to see evidence of things like waters, exogenous molecules. So I thought I would just give you a quick example of this by showing the difference between an isoleucine side chain and a leucine side chain at 3 different resolution values. So at 1.3 angstrom resolution crystallographic data, you can very easily tell the difference between 2 pretty closely related side chains. Same is true at 1.9 angstrom resolution, although it's perhaps a little less clear. Interestingly, at 2.5 angstroms and below, it starts to become pretty difficult to use the electron density data alone to assign the identity of amino acids. And I think this is really interesting because most people view 2.5 angstrom resolution crystallographic data as not that bad. But it does start to sort of become challenging to draw, I guess, very specific conclusions about the positions of side chains. Okay. This is also true when you're looking at metal centers. This is an example of a manganese ion that has amino acid ligands and some exogenous ligands at 1.3 angstrom resolution. You can very easily tell the positions, coordination modes of amino acids, and you can very easily observe exogenous ligands like water. The same is true at about 2 angstroms. At 2.5, it starts to get a little bit more difficult. It becomes difficult to tell if things like carboxylates are mono or bidentate. Presence of waters starts to become a little bit more difficult to ascertain. And so I think these things are important to keep in mind when you're evaluating crystallographic data. Okay, so I thought I would maybe talk just a little bit about how the information that we extract from a diffraction pattern relates to what's going on in your crystal. And I'll do this sort of with the frame of reference of describing how we determine the resolution limit of a data set. So in X-ray crystallography, diffracted rays with strong constructive interference are the only ones that we observe. And we can use Bragg's law to understand exactly which types of rays are observed in our diffraction patterns. So I think it's important to keep in mind that X-rays have their waves. They have 3 key properties: amplitude, frequency, and phase. Constructive interference increases amplitude such that we can observe it in a diffraction pattern. So Bragg's law states that if you divide a crystal into parallel planes of atoms, you can use this to explain the observation of diffracted X-rays with strong constructive interference. Conditions that, or planes, I guess, that satisfy Bragg's law, where lambda is the incident wavelength, or wavelength of the incident X-ray beam. DHKL is the spacing between these planes, and theta is the angle of the incident beam relative to these planes. Satisfaction of these conditions is what leads to an observable reflection in the diffraction pattern. So a macromolecular crystal lattice can be divided into many different regularly spaced sets of parallel planes. These are indexed based on the number of times the planes intersect the unit cell on each A, B, and C edge. The notation of these planes is HK and L values, and these correspond directly to the index of the spots that we see in the diffraction pattern. So this is the connection between what we see in a diffraction pattern and what's going on inside your crystal. So it's perhaps easiest to understand this in a 2-dimensional example. This box is our unit cell. 2, 3, 0 set of planes intersects this edge twice and this edge 3 times, and this is an example in 3 dimensions, and this is actually what's going on in a macromolecular crystal. And so if the indices of our spots increase as we move to the edge of the diffraction pattern, spots with a higher index correspond to planes in the crystal lattice that are more closely spaced. And that's why spots that are higher from the origin provide more detailed information about the electron density of atoms that lie on those planes. Okay, so another thing that we can do, or another piece of information that we can extract from an initial X-ray diffraction pattern is the dimensions of our unit cell. The spacing between spots in a diffraction pattern is inversely proportional to the dimensions of the unit cell. Okay, so there's really 3 pieces of information that we can extract from a first screening of a crystal. We can get the unit cell dimensions, we can understand the lattice type, and we can get some idea about the resolution of our data. And this is actually really useful in deciding whether or not it is worthwhile to collect data on a given crystal. One thing that we'll do in the hands-on activity is perform a Matthews coefficient calculation, and this is I guess a calculation in which we use the unit cell dimensions to estimate the number of residues that are present in the asymmetric unit. And this provides very useful information for moving forward with structure solution and phasing. It tells you how many molecules are present in your asymmetric unit. It also gives you a first measure of whether or not you crystallize the right thing. If you are trying to crystallize a really big complex, but your asymmetric unit is really small, that probably means that something is going on. It's named after Brian Matthews. This guy he's a crystallographer at the University of Oregon. He's the #1 contributor to the PDB. That's because he works on lysozyme, which is widely believed to be the most easy enzyme to crystallize. Okay, so an X-ray data set is not just one diffraction pattern image, but it's an entire set, and we collect this as we rotate the crystal. The reason we do this is because when you collect just one diffraction pattern, you're missing many reflections, and the goal of a collection of a full data set is to not only get a full and complete set of all of the possible reflections in your crystal, but also to get a redundant set of those reflections, so that you have good signal to noise and very accurate measurements of intensity. Important parameters during data collection are the oscillation angle. Not only do you collect a data set or collect a diffraction image from your crystal, rotate it, collect another, and so on, but you also rotate your crystal as you are collecting data, and this also helps capture unrecorded reflections. So this angle is important. This is typically either half or 1 degree. The total number of images that you collect is important. This is actually determined by the symmetry of your crystal. The lattice type will give you information about how much data to collect to get a fully complete set. The exposure time is another important variable. This is particularly important for bioinorganic systems, but it also, overexposing your crystal decreases data quality in general. So it's something that most people are cognizant of. And then the detector position is the last important variable. And the position of the detector determines the high resolution limit of your data. Okay, so the goal is to collect a fully complete and redundant set of reflections and their intensities. Diffraction patterns are never reported in a crystallographic manuscript, and instead we use statistics gathered on the entire data set to judge the quality of the diffraction data. So I'll tell you just a little bit about some of the statistics that we use, and this will, again, be important in the tutorial. Data sets, crystallographic data sets, are very large. They're often on the order of 1 to 10 gigabytes a piece, and so a practical consideration in crystallographic experiments is how do you store and take care of all that data. Okay, so a couple of the things that we do during data processing. First step is usually to index or catalog the positions of all the spots in a diffraction pattern, assign the lattice type and the unit cell. The next step is integration of all of the spots, and then scaling, analysis of statistics, and then finally assignment of space group and determination of the resolution limit. And at the end of all of this, what you wind up with is just a single text file that contains a list of all the reflections and their intensities. So you go from something that's very big, number of high-resolution images, to just a single text file. So an important part in analyzing the statistics associated with data collection is binning the data by resolution. And so for a diffraction pattern, what you do is you draw concentric circles that correspond to specific resolution limits. This is some of Tom's data. It goes out to about 1.8 angstrom resolution. And you compile statistics, not only for the overall data set, but for these individual resolution bins. And this is actually, comparing statistics for individual resolution bins is what helps you decide what the ultimate resolution of your data set is. So there's really 2 different types of statistics that we compile. One, I guess, tells you about the information content of a given resolution bin in the overall data set. And for this, we compare intensity of all the spots in a given resolution bin to its background. If this value is greater than 2, it's I guess, generally considered to be acceptable to include that resolution bin in the ultimate data set or the final data set. The other type of measure, our statistic, this is a measure of intensity differences between reflections with the same index. And so it's a value that ranges from 0 to 1. If you have 2 different spots of the same index, they have the same intensity, our statistic is 0. If they're totally different, then it's 1. And for the overall data set, I guess the standard is usually that they should be no more than 10% different from each other. Okay, so this is an example of a data table from a paper. This is actually from the protein that we will work on in the tutorial. The statistics are usually broken down into the overall, so this is a number that's not in parentheses, and then the number in parentheses is for the highest resolution bin. Completeness, I over sigma, are these information content statistics. In this, they actually don't conform to my greater than 2 value, but the rest of the statistics are really good. The R value here is 5% for overall. It's usually higher in the highest resolution bin, and that's acceptable. I think 30, 40, 50% is standard. Okay, so how do we go from diffraction data to an electron density map? We use structure factors to relate diffraction intensities to electron density and then ultimately to atom position. I think an important concept here is that structure factors can be computed either from diffraction data or they can be computed from atom position or from the molecular model. And this is something that we do I guess extensively during crystallographic refinement and even during structure solution as we compare structure factors computed from atom position in model undergoing refinement and those computed from the diffraction data. And when those start to match up, that's a measure of the validity of the model. So each reflection, each index spot in the diffraction pattern can be described by a structure factor function. And each structure factor that corresponds to a reflection is the sum of the diffractive contributions to that spot from all atoms in the unit cell. And so this is the equation that we use to generate structure factors from atom positions. And this really only depends on the atom position, XYZ value or XYZ coordinate, and an atomic scattering factor, and this is determined by the type of atom. Okay, so an electron density map is a 3D plot of a Fourier sum that contains structure factor function. And we plot this from diffraction data by computing the structure factor as a periodic function, as an amplitude, frequency, and phase. Amplitude we can get from diffraction intensities. The frequency is related to lattice plane spacing, and that's also something we can get from the diffraction pattern. The phase is something that we lose in the data collection process. And this is a really important issue. Every structure that's solved has to generate this phase information somehow. Okay, so this is actually really important if you perform same mathematical transformation on this little cartoon duck, get a diffraction pattern essentially, and do the same thing on this cat. You take the phase information from the cat and apply it to the diffraction pattern of the duck, you get back the cat. So the lesson to be taken from this is that the phases contain most of the information that's necessary for structure determination. So solving the phase problem is something that is really important to do well, I guess. So there's really 3 methods for doing this: molecular replacement, anomalous diffraction methods, and multiple isomorphous replacement methods. These can be combined, and there's some more complicated I guess, combined methods for doing this. And you can also do this directly with very small proteins. I won't talk at all about that because there's really very few, I guess, samples where that's appropriate. So molecular replacement is probably, in practice, the easiest. And it's simply where you use a similar protein of known structure to compute phase information from the positions of the atoms. It typically has to be 30% or greater, 30% identical in sequence or more. Structure also has to be very similar in addition to that, obviously. The advantage here is that the structure can be solved from a single native data set. You don't need to collect additional crystallographic data, but it is susceptible to bias, and it only really works in a limited number of situations. If you have a completely new structure, this method will generally not work. So the other two types of phase determination, I guess for that reason, are known as experimental phasing methods. These use heavy atom sites, transition metals or halogens in some cases, selenium in crystals, and these can be either added artificially or they can be present as native cofactors. In this method, you collect data such that you're able to determine the position of heavy atoms in the unit cell, and then you use phase information associated with those heavy atoms to compute protein phases. And I'll talk a little bit about how this works. This is generally viewed as a more difficult method for phase determination because it requires collection of multiple crystallographic data sets, multiple diffraction data sets, and in many cases it requires being able to generate more than one crystal. This generates an electron density map without a model, so you have to build in from scratch position of every amino acid in the model. And this is something that we will do during the tutorial. Okay, so in anomalous diffraction methods, you take advantage of the fact that things like transition metals, selenium, absorb X-rays. So this is a principle that we have heard about already this week. And this alters diffraction intensity in such a way that you can use those differences to locate heavy atoms in the unit cell. You have to collect your data set near the heavy atom absorption edge, and this usually means that you have to use an X-ray source that's tunable. These are really only available at synchrotron sources. It's most typical, I guess, to use selenium as selenium at substituted proteins as the anomalous scatterers, but for bioinorganic systems, native metal cofactors can also be used. And this is actually a very nice, I think, advantage in crystallography associated with metalloproteins, that you often don't have to derivatize your system to solve a structure experimentally. So the basis for anomalous diffraction experiments takes advantage of the fact that a principle called Friedel's law, where sets of planes that have the same index but with opposite signs, in the absence of an anomalous scatterer, will generate spots in the diffraction pattern that have equal intensities. If you have a transition metal present or something that absorbs X-rays at the wavelength that you're collecting data at, this is no longer true, and you can take advantage of that difference to solve the structure. Isomorphous replacement is based on the same principle, but it relies on artificial incorporation of heavy atoms into the crystal, and it I guess, relies on comparison of a crystal that is not derivatized to one that is, and the differences in intensity that you observe are present in every spot in the diffraction pattern, not just Friedel pairs. This is viewed as, I think, the most difficult way to solve a structure because it typically requires many crystals. Heavy atoms have to bind to the same site in every crystal or in every molecule in the lattice, and the crystals have to diffract exactly the same as the native after you incorporate heavy atom. It's termed as being isomorphous. So the basis for experimental phasing in both isomorphous replacement and anomalous diffraction methods is the same. And And I'll go through this just a little bit. This is, I think, for me, this is not very intuitive, and I think I'll go over the mathematical basis for it and tell you a little bit about how it works. But I think understanding the process will become more clear in the tutorial. And it turns out that actually all of this is performed by computers. Crystallographers don't have to go in and solve the phase problem by hand. You just have to know if it worked. And it's actually pretty straightforward to understand if phase determination was successful. So the basis for this, it's probably easiest to explain if you represent structure factors as vectors, in which the length of the vector corresponds to the amplitude of the structure factor. So this is something that we know from diffraction data collection. It's associated with or proportional to intensity. And the phase is represented as the angle of this vector relative to the axis. So in an isomorphous replacement experiment, this is probably the easiest way to describe it at first. You have a structure factor associated with your protein that does not contain a derivative. You have a structure factor associated for the protein plus the derivative. And the structure factor for the protein without the derivative, which is the value that we're interested in computing, the full value with its phase information, is equal to structure factor for the derivative minus the structure factor of the heavy atom alone. And this is important because the structure factor of the heavy atom alone is something that we can determine experimentally, and it turns out that we can use that information and this relationship to compute the information that we want, the phase information for the protein structure factor. And so you can represent this using vectors by laying all three of these head to tail, and because of this equality, they form a triangle. Okay, so in a phasing experiment, I guess of these three vectors, the one that we know, both its amplitude and its phase, so its length and its angle, is the heavy atom structure factor. The derivative structure factor, we know its amplitude, but we don't know its angle. And so what that means is that you can draw a circle, and this vector lies anywhere on that circle. Same is true for the protein structure factor. If we start at the origin and draw its length, it can also lie anywhere on this circle. And because of this equality, where these circles intersect, there are two possible solutions for the full structure factor for the protein. It's called Harker diagram. So this provides two possible solutions. In multiple isomorphous replacement, you can resolve phase ambiguity by determining or collecting data on an additional derivative. You can draw more circles and get a single answer. Okay, so I'll talk just a little bit about how we determine heavy atom location in both multiple isomorphous replacement phase determination as well as in anomalous diffraction experiments. Mostly talk about this because this is something we are going to do by hand in the tutorial, so I'll give you just a brief introduction here in a very simple example, and then we'll do something more complicated in the hands-on activity. So a Patterson function is the method by which we determine the position of heavy atoms using either multiple isomorphous replacement methods or anomalous diffraction. And this is it's actually very similar to the function by which we compute an electron density map, except that it doesn't require phase information. It can be computed from the amplitudes of structure factors alone. And what we actually look at in both MIR and anomalous diffraction methods is a difference Patterson map. So the outcome of the Patterson function is a contour map, and it doesn't directly report on the positions of atoms in the unit cell, but it instead tells you, instead gives you information about the distance and orientation between two different anomalous scatters or heavy atoms in the unit cell. So it corresponds to the vectors that you can draw between atoms. You determine these vectors by taking advantage of information about symmetry in the crystal. And this also, I guess that it is an important component of using computational methods to determine the location of Patterson atoms. And in fact, what it means is that in 3 dimensions, Patterson vectors are located in specific areas in a 3-dimensional map, and these are called Harker sections. And I guess when you use a computer to look at a Patterson map, this isn't such a big deal, but I think this was a really big deal when you had to print these out and determine the locations by hand. But this is something that we are going to do in the tutorial, so also something that we have to think about. So I came up with a really simple example. This is not very intuitive for me. This is, I guess, sort of an artificial example in that it's a plane group, so it's a 2-dimensional example, and it's in P2. This is really easy because there's only one symmetry operator in this group. And so what I'm showing you here is an example where you have perhaps a single atom in your unit cell, and you're trying to determine its position using the Patterson function. And your unit cell is located at coordinate of 0.1, 0.2. Symmetry operator here is negative x, negative y, and so what that means is that for every atom you have a given coordinate, there's one at negative x and negative y, so here it would be negative 1 at 0.1, negative 0.2. So Patterson map for this system would look something like this, where you have a peak at the origin, and then you have a peak not at x and y, but at one that corresponds to the distance and the difference in orientation between these 2 atoms. And you can compute that by just simply subtracting the symmetry operators from each other, and this tells you that you would expect a peak at 2x and 2y, where x and y are the positions of the heavy atom in the original unit cell. So in determining heavy atom positions using a Patterson, you sort of work backwards here. First step is to assign Patterson peak coordinates, select an appropriate vector. Here there's only really one, and then solve for x and y. In the tutorial, we're going to do this with multiple sites, 3-dimensional space group, and more than one option for the Patterson vector. But the simple procedure that you use here is what we'll use in the tutorial. Okay, so in anomalous diffraction methods, we take advantage of the fact that transition metals, selenium, halogens, absorb X-rays, and I think an important practical component to structure solution by this method is that all of these entities absorb X-rays at wavelengths that are accessible using synchrotron radiation sources. So you're able to tune the beam to a value near the absorption edge, and this leads to observation of differences in intensities between Friedel pairs, and you can use that to solve the phase problem. And this is actually really very conceptually similar to what I described in multiple isomorphous replacement, where you have structure factor that you compute using data collected at one wavelength, and this wavelength is usually selected such that there's no contribution from anomalous scattering. Collect data at a second wavelength where there is, so something near the absorption peak of the element that you're using to solve the structure. And here you also have, you can also equate these structure factors using the anomalous scattering factors for the heavy atom, except here they're broken down into real and imaginary components, so you have 2 instead of 1. You can also use information about what we know about the relationship between Friedel pairs, structure factors associated with Friedel pairs, that they're equal in intensity with phases opposite in sign when there's no anomalous scattering, but that they do in fact have differences in intensity, and that this is due to a change in the imaginary component of the scattering factor. Magnitudes of anomalous scattering contributions are known quantities based on the identity of the atom largely, I think, and its phase depends only on atom position. So you can use a Patterson function to locate where it is and compute phase information from that. So you can do the same thing where you draw, you know the positions of the anomalous scattering factors the full structure factor information, and then you can draw circles associated with the intensities of the protein structure factors at each of the two wavelengths that you've collected data at, and where they intersect, provide possible solutions to the phase problem. Data collection at additional wavelengths allows you to draw more circles, and this improves the phase estimate. Usually you can do this, or you can get different information because the magnitudes of the anomalous scattering factors vary according to the X-ray wavelength. And so I'll talk just a little bit about how you select wavelengths, because the exercise that we'll do in the tutorial is a multiple anomalous diffraction experiment with data collected at 4 different wavelengths. So usually the wavelength that has the maximum anomalous scattering signal is right or close to the absorption peak. This is an X-ray fluorescence scan. Wavelength 2 is usually chosen at the value or the inflection point of the edge, and additional wavelengths are chosen to be either below the absorption edge, so this is where there would be no anomalous scattering. You can also collect what's known as a high remote data set. Usually a high remote or a native data set is selected, especially if you are using a transition metal anomalous scatterer, where the energy associated with data collection at the absorption peak or inflection or below it are relatively low in energy. There's a wavelength dependence on the resolution of your data. And so usually data collected at the absorption peak for, say, iron or copper or another first row transition metal usually gives lower resolution data than what you would typically collect at a higher energy. And so a high remote is often selected just to give you better resolution. Okay, so I think it's important to keep in mind that the phase problem is much like generating crystals in the first place, a trial and error process. Phasing methods can be combined to improve phase accuracy. Phase information is iteratively improved during model building and refinement. So usually the initial phases determined experimentally are not so good, but they improve as you start to use the model itself to provide additional information about phases. And in fact, in the late stages of refinement, all the phase information typically comes from the model itself. So at the end of the day, all crystal structures are, I guess, molecular replacement. Phase information comes from the same process by which you determine phases in molecular replacement. How do we assess the quality of experimental phase information? How do we know if our phases are good enough to solve the structure? So there are, in fact, a number of statistics that you can use, and we'll talk about some of those in the tutorial. But I think most crystallographers just simply use the quality of the electron density map to determine whether or not the phase information is good enough to solve the structure. If you feel like the map that you get out is good enough to start building in amino acids and determining the structure, then you move forward. Okay, so some issues that can make it difficult to accurately determine phases. Inaccurate measurements of intensity differences, particularly in anomalous diffraction methods, where you're actually looking at very small differences in just a few reflections in the data set. This is a big deal. Things that can cause inaccurate measurement of intensities include radiation damage. You often have to alter your data collection strategy to collect data that is appropriate for experimental phase determination. Low redundancy or completeness, if your crystal sort of dies during data collection, that can affect the ability to determine good phase information. And finally, low occupancy of heavy atom sites can be a big issue. So just a few examples of other ways that you can use anomalous scattering information to gain information about bioinorganic systems. This is a project that I worked on as a postdoc with Laura Gisamo, who's here at the workshop, from Marty and Karsten's lab here. This is a structure that we determined of the manganese-iron cofactor in class 1C ribonucleotide reductase. And we used basically the same methods that you use to locate heavy atom sites for phase determination to calculate anomalous difference maps that were metal-specific for manganese and iron and locate or determine which site in this cofactor is occupied by manganese and which by iron. This is something that several other groups did with this system as well. It turned out to be actually pretty tricky to figure out how to do this. And the thing that worked the best in our hands was to simply add just one equivalent of manganese, one equivalent of iron, and allow the system to crystallize anaerobically. This provided some really important information, I think, actually, about how this type of cofactor is assembled in vivo. Another really interesting system, this is actually a technique that was developed in Oliver Einzel's lab, and it allows for I guess, elucidation of oxidation state information in crystals that contain multiple metal ion sites, and they applied this technique to nitrogenase. It's actually a very challenging system because it contains there's two different very complex metal clusters, and then they also used it to understand the oxidation state and to identify an additional mononuclear site in this protein. And so in this method, what they do is they collect wedges of data at different wavelengths on either side of the iron absorption edge, and they use that data to calculate individual scattering factors for each of the individual irons in the structure. And they plot those out and compare the edges to known models, ferrous and ferric iron. What they're able to determine is that the mononuclear site that they obtained or that they identified in this structure is more similar to an iron 2 model. FeMoCo is also very similar, and the P cluster is different. I think this is exciting because this is, I think, something where previously most people probably would have said that crystallographic data not useful in understanding, particularly in complex metal clusters, oxidation states of individual ions. And it's interesting to think about how this type of thing could be applied to other systems. Okay, so once we've solved structure and determined phase information, we can compute an electron density map and generate a macromolecular model. There's, I guess, three steps associated with model building: interpretation of the map, refinement of coordinates, and these two steps, crystallographers sort of iteratively move back and forth between these. And then once you've landed on a final model, last step is to validate it and compare it to other protein models, similar resolution, and things like that. Okay, so we use this equation to calculate electron density maps. I guess the key inputs here are structure factor amplitudes, and we can either calculate these from intensities from diffraction data, or we can also calculate them from the positions of atoms in the molecular model. And then phase information either always comes from the model itself or from experimental phase information. There are two different types of maps that we look at. 2FO FC map is actually a combination of observed structure factors and calculated structure factors. It's a single color molecular surface map that usually corresponds to the contour of your model. And then the second, I guess, common type of map that crystallographers look at and use in model building is FO minus FC electron density map, and this is a difference map. It highlights errors in the model. See positive difference density where there are features that should be in your model. The X-ray data suggests that there should be atoms present in the model, but there currently aren't. And then negative difference density is present where there are things in your model that shouldn't be there. Okay, so this is the type of information that you would get from a de novo structure solution, experimental phasing structure solution. And in the tutorial, this is the type of map that we'll get out of the structure solution process. So in blue is the 2FOFC map. So it's a single continuous contour, and you can kind of start to pick out features like backbone and side chain. Red and green, the difference map. I don't think there is actually any red here, but the green density is here. And in this model, these are actually probably water molecules. And so in map interpretation, what we do is we use modeling tools to place amino acids or other features of the model into the electron density. And then we refine the positions of those atoms and compare to the electron density map to determine whether or not we are correct. So the refinement process is a computer-assisted way to improve the agreement between the model and the diffraction intensity data. And what we do is we refine specific parameters to improve the agreement between calculated structure factors and those calculated from the diffraction intensities. And I believe we, in fact, compare the amplitudes only. So the parameters that are typically used are the atom positions themselves, temperature factors, and in some cases the occupancy of the atoms. Occupancy is actually a really important parameter in metalloproteins or systems that use or that have metal cofactors, and occupancy can be refined automatically. There are several tools out there to do this, or you can also just do it by visual inspection of the electron density map. Okay, so it's two classes of metrics that are used to evaluate the quality of the molecular model, or how well does the model predict the X-ray data, and that's determined by the R factor or the R free. These are similar in that they compare calculated structure factor intensities to those observed in the X-ray data. The R free statistic is computed from a subset of data that's left completely out of the refinement process, so it's viewed as a more unbiased measure of evaluating the model. And these are the R and R free statistics are reported in crystallographic manuscripts, and the metrics that people use to judge how good these statistics are. R is typically between 0.1 and 0.3. It's dependent on the resolution of the data, however, and it should be within about 5% of the R free value. The closer that they are, the better. Okay, so the other measure that people use to evaluate crystallographic data is how well does it conform to known geometric parameters about proteins or nucleic acids, things like RMS deviations from typical bond lengths and angles in amino acids and peptide backbone. We use Ramachandran statistics to evaluate how well it conforms. There are also a number of newer metrics and other validation tools. I think an important thing to remember, though, is that even though we typically report these statistics for the entire model, the model quality is also a local property, and I think this is why it's important if you are using a crystallographic model, or to keep in mind if you are generating a crystallographic model that someone might use one day for something else, that it's important to go in and evaluate the quality in specific areas of the structure that are important to you or that are important in general. I think it's important. I guess it's an important responsibility for crystallographers to be upfront about areas of the structure that are of poor quality relative to the rest of the protein. So there are some tools out there for evaluating models that are in the PDB or your own models. The Molprobity server is a good tool. There is a actually very recently revamped validation server associated with the PDB that I think is also very good and actually does many of the things that Molprobity does. There's a whole set of other resources available on the PDB website. Okay, so these are really all of the things that you have to go through to solve a structure, and we will do many of these in the tutorial. I think I'll stop here and take any questions if you have them. Thank you for your attention. Yeah. Yeah, so in fact, I think this is actually a very, very exciting type of crystallographic experiment. You can do things like take an enzyme, add a substrate, and it will often still be active in the crystal. And I think there's this idea that the packing and the level of solvation in a crystal is actually very similar to the environment inside a cell. And most catalytic systems are still functional, and things are in fact very dynamic at room temperature, at least. Yeah.
You said that the actual X-ray diffraction data is never reported. Is the text file that comes out of that reported, or is it only the electron density map?
So structure factors or structure factor intensities are reported, or they must be deposited in the PDB, I guess. But yeah, but that's actually a relatively new phenomenon. So if you go back and look at things that are like 15 or 20 years old, they often don't have deposited structure factors, and it's only the coordinates that are available for viewing. But because of that, you can actually go in and look at the electron density map, and there is some connection back to the actual diffraction data.